Hi everyone, thanks for checking out this video. So this is going to be another video in this series I'm making on parameter estimation. And this is actually kind of a sequel to another video I made. So I previously made this video on how to use SciPy to estimate parameters of probability distributions. So I made that video and a bunch of commenters pointed out that the way I described to do things in that video um, only works for continuous distributions in SciPy, and it doesn't work for discrete distributions. So just to remind you guys of that, continuous distributions have this like very easy method you can use in SciPy that's called the fit method that you can just easily use to fit the distribution to your data set. And so in my previous video, I showed you guys how to use this method, but then as the commenters pointed out, I didn't realize SciPy only has this for continuous distributions, and for discrete distributions, um, they don't have this like nice convenient method. So it's like they make it like really easy to do for continuous distributions, but for discrete distributions, we have to kind of do the parameter estimation ourselves. So this video is going to be showing you guys how to do the parameter estimation for a probability distribution, like kind of from scratch, if we don't have this this nice fit method that SciPy gives us for the continuous distributions. So this is going to be showing you guys, how to do it kind of from scratch in a way that'll work for any kind of distribution, even discrete distributions. Okay, so I'll kind of give you guys like the example data set we're talking about here. So let's say that you're a restaurant owner, and every day you count the number of customers who come into your restaurant. And let's just say, for making a simplifying assumption, let's just say that the only difference between days is random fluctuation. There are no days that are like more busy or less busy as part of a pattern. It's only random fluctuations between the days. But yeah, so every day you count how many customers come into your restaurant, and then you make this this plot of your data after collecting for like 3 years or so. And then so this is the number of days that you counted for every possible number of customers. So it says that like this is how many days you had 0 customers, and then 1 customer, and then this is how many days you had 2 customers, like 75 days, and so on and so on. So this is a discrete distribution because you can't have like 2.3 customers on a given day. You know what I mean? All of these data points are integers. So this is what we call a discrete distribution. And so this is what the data actually looks like. This is just all of our counts for all the days. This is the data set here. And then we need to think about how we're going to fit this to a distribution. So this is the point where this is actually the hardest part of this kind of work, is you need to develop some kind of intuition for what distribution you should even be using in the first place. So in this case, we're going to use what's called a Poisson distribution. So a Poisson distribution is used to count the number of random occurrences either in a time interval or in a physical space. So for example, a Poisson distribution could be used to model the number of visitors to a website on a given day, or like we're doing the number of customers in a store on a given day, or like possibly the number of calls that a call center gets. So there's just a couple examples, but use a Poisson distribution to model the number of random occurrences that occur in a given time interval or a given like physical space. But yeah, so this is kind of the hard part, is just you kind of have to develop the intuition to know which distribution you should be using. But for this one, I'll just tell you guys we're going to use a Poisson distribution because we're trying to model the number of occurrences that are happening in a time interval. But yeah, so we're using the Poisson distribution. But yeah, it's like I said, we can't use this convenient we can't use this convenient fit method because the Poisson distribution and I think all the discrete distributions in SciPy don't have this. So I need to show you guys how to fit the data kind of from scratch without using this like nice easy method that they give us for the continuous distributions. But okay, so let's get started. So the first thing we do, like usual, is just import all the libraries we're going to be using. So going to be using matplotlib, SciPy, the CSV library, NumPy, and then actually this is a library I use for like debugging purposes. But I mean, we actually don't even need this, to be honest. Okay, so the first thing we're going to do is read in the data. So I'm going to be a little bit lazy here and just copy and paste this part of the code, because if you guys have been watching my previous videos, you should kind of have an idea of like how to read in a CSV at this point. But I'll kind of like show you guys what everything's doing here anyway. So we're just defining an empty list to store our data in. And then we're opening up the CSV file that I just showed you guys. It's called CSV. There's only one column of data, so there's not actually any commas in this file. But if we did have more than one column of data, we'd be separating them with commas. That's what's called CSV. But yeah, every row here is just one data point. And then we're just going to define our CSV reader, and then iterate through our data set and append all of these data points into our data list. So we'll be filling up this empty list with all these data points in our CSV file. And it's very important. Make sure you're casting the data points into a number type. So you should cast it into a float, or really in this case, you could cast them into ints because all of these are integers. But I just said float because I want to keep it consistent so that you could do the same thing for a continuous data set that wasn't all just ints. But in this case, you could cast it to ints, but I'm just gonna keep them as floats just to keep this so that it can be generalized to lots of different kinds of data sets. Okay, so now let's just plot our data and make sure that we've read it in correctly and it looks the same as this plot here. So yeah, we're going to say plt.hist, getting a histogram here of our data, and then bins equals int np.max data. So this is just a way of saying that we want to look at like whatever the highest number is here. We want that many bins so that we have one bin per possible number of customers. So that's just kind of a complicated way of saying that. And then density, and then alpha equals 0.5. That'll just make it well, you'll see why we have that later, because this is just making the bars somewhat transparent so that we can later plot another plot on top of it and be able to see this other plot. But yeah, so just kind of trust me on that one for now. But yeah, okay. So let's just see what this gives us. Let's just see if we've read in the data, okay? Yeah, so it looks good. Looks like how it's supposed to look. So it looks like we read it in properly. And then again, we've just set this like density to be true so that we're not seeing the number of occurrences anymore. We're seeing like the actual like probabilities on the y-axis. But yeah, I mean, basically we just want to check and see, like, make sure it has the same like overall shape as this this original plot. But yeah, so it looks good. So we can continue on. I'm just going to comment that out for now. And then so the next thing we're going to do is, like we've been doing with all of these parameter estimation videos, we need to define some loss function. And the loss function is going to be what we're going to be trying to minimize. I'll just tell you guys too, since we're dealing with a Poisson distribution, I should have even mentioned this earlier. With the Poisson distribution, like, it has a special quality where it only has one parameter, and the only parameter is the mean, and then the variance is actually equal to the mean. So in the special case of a Poisson distribution, actually the easiest way to fit the distribution to your data is to just take the mean of your data, and then that's the only parameter you need for the Poisson distribution, because it only takes the mean parameter, and then the variance is just equal to the mean. But that's like a special quality of the Poisson distribution that's not true of other distributions. So even though that's the easy way to fit a Poisson distribution to data, is to just take the mean of the data, and that's the only parameter you need. I want to show you guys a way to fit a distribution that can be generalized to other discrete distributions. So even though the Poisson has this like easy way to do it, I'm going to show you guys a slightly harder way that can be generalized to other kinds of discrete distributions. But yeah, so like I was saying before, it's like what we've been doing with all these parameter estimation videos is defining a loss function that will quantify how far off our model is from the data. And then once we have that loss function written, the only thing we'll need to do is find the parameter values that minimize that loss function, because that'll be minimizing how far off our model is from the data. So yeah, the tricky thing with all of these is to just write a loss function, and then you can just easily find what parameter value minimizes it. So yeah, we'll just start here. Define loss function. Params. Like I said, we only have one parameter we need to find here. It's just this mean parameter that's also equal to the variance parameter. But again, I'm trying to make this lesson in a way that this same method can be like generalized to other kinds of discrete distributions. So I'll assume as if we might have to deal with like more than one parameter. So I'll just, instead of passing in the actual number, I'll pass in an array of params that in our case will only have one number in it, but it could have like more than one parameter if you wanted to, if you're dealing with a different kind of distribution with more than one parameter. But yeah, so I'll pass in some array of params, and then we're going to pass in our data, which I'll just call data underscore in. And then let's just save our in this case only one param. It's kind of like a convention to call this parameter mu when you're dealing with the Poisson distribution. We call this mu for like the mean parameter, and this is also in this case, like I've been saying, this is also equal to the variance. But yeah, we'll just call this mu for now. You guys can call it anything, but I'm just going to call it mu. And then we'll start our loss off at 0. And then, like we've been doing in all these other parameter estimation videos, the idea is to iterate through all of our data points. So I'm going to say for I in range len data in, going to iterate through all of our data points. And then so here's where we're going to be using a method that might be kind of new for you guys. We're going to be doing something called the log likelihood method. And in the future, I might make another video going like more in depth on like the theory of this and like kind of like probability theory, like why this makes sense to do and like what we're actually doing here. But for now, all you need to really know is that the log likelihood is you basically take the probability of observing your data point given some underlying distribution. You take that probability and then you take the natural log of it to just make the number like easier to work with, basically. So if that doesn't make sense, yeah, I may make like a more in-depth video on this method in the future. But for now, all you need to know is the log likelihood is a measure of how likely it is to see your data point given some underlying distribution. And we're basically taking the log to make the numbers just easier to deal with. But yeah, the way we're going to write this is log likelihood equals SciPy dot stats dot Poisson dot log PMF. This is the natural log of the probability mass function. So we want the log PMF of our data point, which is data in index I, because we're using I to iterate through all of these data points. And then the second argument here is the is our mu parameter, which will be the parameter for the underlying distribution that we're checking. Yeah. And so this is all you need here. This is basically just, again, just to repeat myself, it's just giving you a measure of the likelihood of observing this data point given some underlying distribution with parameter mu, which is the parameter that we're testing. Okay. And then so the next thing to do is, since this is a loss function, like this is a measure of how likely something is. So the likelihood is like a good thing that we're trying to maximize, but just for the sake of convention and keeping things consistent across videos, instead of making this a likelihood function, I've called it still a loss function because I'm just trying to keep things consistent with my other videos. So in order to get the loss, we just want the negative likelihood, basically. So I'm going to say loss to add equals negative log likelihood. Because we could just add up all of the log likelihoods and then try to maximize that. But just to keep things consistent, I'm going to still talk about loss as something we want to minimize. So I'm just going to say the loss to add is the negative log likelihood. And then, yeah, so loss plus equals loss to add. Okay, so just to repeat myself again, this is just going through all of our data points and then calculating this measure of log likelihood for observing this data point given some underlying distribution with parameter mu. And then we return the loss at the end. So just to remind you guys, just sorry if I keep repeating myself up, but I just want to like stress the main point of parameter estimation here is we basically have written this loss function to basically give us a measure of how far off the model is from our data given some parameter. And then the goal is to find the parameter value that minimizes this loss function, because that will be the parameter value that minimizes how far off our distribution is from our data set. Okay, so that's like writing the loss function is kind of the hard part, and now from here it's kind of an easy thing to do the actual minimization. So the first thing we're going to do is just say what parameter we're starting off with as a guess. So call this param 0. Let's just start off with 20 as our first guess. And like I said, I'm kind of making this like needlessly difficult because with a Poisson distribution, like you don't even have to do any of this. You can just find the mean of the distribution, and that will be the parameter of the distribution, because it only takes the mean parameter. There's nothing else you have to worry about. But I'm kind of just making it complicated so that I'm showing you guys how to do it in a way that will generalize to other discrete distributions. So again, here I'm gonna make it hard on the computer just to show you guys that it will actually work. So instead of guessing like 4 or like 5 or 6 or something, I'm just going to guess 20, which we know isn't even possible. But I'm just going to guess 20 just to show you guys that this minimization will like actually work. So I'm kind of like making it hard to just to kind of prove a point here. And then so the next thing we're going to do is say minimum equals SciPy dot SciPy dot optimize dot fmin. This is like a SciPy minimization function. And then we're going to minimize our loss function. Just, you guys can call it whatever you want. I just called it the loss function to keep it simple. But just whatever you named your loss function, that'll be the first argument. And then our params guess is the second argument. And then we need to actually pass in our data. So here we're going to say args equals parentheses data, comma. And we're saying data here because that's what we called our data that we were reading in, called it data here. So we're passing in that list of data there. So then this will give us our results of this minimization, and then we're just going to say mu fit equals minimum the first element of it. That'll give us our fit value of mu after doing this minimization of the loss function. And then we'll just print that out. We'll say mu fit, and then so that we can see what the actual result was. Okay, so once you guys have done this, this should hopefully be enough to fit your data to the distribution and get out what parameter accomplishes that fitting. But just to show you guys that it works, I'm also going to plot the results of this. So I'm going to plot the results, and again, just being a little bit lazy, copy and pasting in code. But this is basically just plotting a scatter plot of the Poisson distribution with our fit value of the parameter. So this is, we're going to plot this on top of the actual data. So we're going to plot this plot again, but on top of it, we're going to plot our fit distribution using this mu fit that we're getting out of this loss function minimization here. Okay, so let's see if this works. Okay, so it looks like it worked okay. So we have our data histogram that I showed you guys before. And then on top of that, we've plotted the Poisson distribution for our fit value of mu. And it's kind of like I was telling you guys, this is a discrete distribution, so that's why it's a scatter plot rather than a line, because it's only the only possible values of it are integers, so that's why I've plotted it as a scatter plot. But we can see that with our fit value of mu, it does fit the distribution like reasonably well. And then we can also look at the results. So the mu fit value that we got out of it was like 4.968 something. So that's our fit value of mu. And then now, like I've been doing, I'll show you guys what value of mu I actually used to generate this this data set we've been using. So the actual value of mu that I used was 5. So we can see that our parameter estimation got pretty close. The real value of mu was 5. The fit value of mu was like 4.9 something. So it did pretty well, got pretty close. And again, like I've been saying, I mean, with the Poisson distribution, you don't even have to do all this work. You can just take the mean of your data, and that is your mu fit value. But I sort of showed you guys how to do all this with like the log likelihood and the loss function and stuff, just so that you can use it for other discrete distributions besides just the Poisson distribution. So for other ones like the geometric distribution or like the binomial distribution or something, you can apply like this same kind of method for those too. Okay, so thanks for watching, and like usual, the code will be on my GitHub if you want to download it. But yeah, if you guys have any questions, just let me know in the comments. And thanks for watching, and see you next time.